Thank you very much for the opportunity. So my talk is building a fully traceable or outside of plant network for future 5G, Internet of Things, and the NG-PON2 all together. So my talk involves 3 parts. The first part is the current mode of operation for the network, and of course touch base of the 3G for 5G to 4G, 5G, the advancement, and the OSP visibility. And the second part is the technology availability, and what is practical, what is needed, and how can we deliver that. And the cost is always embedded into that equation. The last part is what we want to talk about is what we have accomplished, not just Go Foton, but the entire industry, what we have accomplished. So take a look of this picture, and this is just a city with surroundings. And this is a current mode of operation. And for us, if you look at deep, this physical domain is so massive and also very fractal in nature. And the current mode of operation, if you truly look at the outside plant versus the CO, and the CO, the equipment is just a subdomain, very small. And how can we cover this such a massive network for all the connectivities? And how can we do that? And that is 5G advancement. And also, we needed visibility. So the fiber optic network evolution history, I'm touched a little bit based onto that. And as everybody knows, the 3G to 4G and the 5G is really, in terms of technology, bandwidth coverage is really revolutionary rather than evolution. So the question, time over time, people will ask, do we have enough fiber? This has been this way for the last 20 years, but very little touch base about do we have enough connectivity, terminations. Of course, you know, for fiber, without have the capability to be terminated, it's just useless, cannot do it. So each fiber, it's even a long spool, a bigger spool you deploy it. In its lifetime, you will have many fiber cut. You have to be able to splice and also to maintain that insertion loss and the rest of performance. And let's look at the technology revolution side of it. So everybody knows the massive MIMO and the fiber, cable, of course the termination, and how can we expand. The next part is latency. We are so used about the sonata world is 50 milliseconds for the timing, for the latency, for the network protection. But for the 5G, the latency is really come into 1 to 5 milliseconds. And this is the demand, is the requirement for the game, automobile, the drones, all those realistic applications. Then comes to the virtualization. So you have the physical work fully built. The next one is expanded the network with its full true potential. And you talk about also many things, people on the market. By end of the day, to the customer, you have a quality of experience, not just the service, quality of experience, how you experience with the service. Then the optimization. The optimization part is how do you manage the millimeter wave and fix the target versus, moving target. How do you handle the being burst, this kind of technology? Then the unlimited applications. The applications basically satisfy each individual subscribers, and we have to think innovatively. How can we deploy this type of network? Now let's look at the traditional network. So we have RODM. I was involved in that, building this type of application. So on the optical domain, we have a perfect fabrication for the RODM. And then next step is the current mode is just using that in the office, in the equipment domain, in the CO. But once we use this building block for the optical domain, fully optical, and build a network, and we have a beautiful architecture drawn, have a ring, mesh, But very little people will talk about how this path, this ring or mesh built, what's involved. It's not a miracle. It's just not in the architecture domain. You draw a line, it will happen. The reality is you have so many terminations, connectivities, and it was, and it still is, assumed that protection, protect and unprotected network architecture were fully covered by equipment. Is this true? Yes, from concept, theoretical, yes, it's possible. But if you really go into the massive network, the picture I just showed you, a big city with all the residential area, all the environment, how can you possibly to cover that such a massive network? And of course, we all know in the past for 3G and 4G, we really fighting for the 6 gigahertz bandwidth about. Now we are open the entire bandwidth, go from 6 to 80, and basically we are fighting for 60 to possibly 80 gigahertz, bandwidth. This is tremendous. And you look at the 5G network, the bandwidth, and also the CRAM, how the base station is built. I think this becomes a very dynamic network infrastructure. So this becomes a very practical network. It's emerging comprehensive optical distribution network with monitoring at every single section. And we really can help for a bigger and meaningful data collections. So you look at that, you can say this is a mesh or ring, and attached to all this, you have the residential, the business, the COs, the data centers, and the trains, the car, automobile, and all kinds of drones and application. Look at this massive network. How can we build it? We first have to take a look. Like we went through the college, we take a look at the calculus, take a limit. So what is our limit? What is the nature's limit? What is our human being's limit? So let me show you a picture. The picture is so advanced in nature. Menoir, he was a French and American mathematician. So he invented called fractal geometry. The fractal geometry, actually, if you study that, it retrofits for all the ancient philosophy about the Fibonacci numbers, golden rules, all this. And if you go from the universe, big universe, or multiverse, and contract it into a bird, the feathers, it's all very fractal. So you can expand it, you can contract it. And then the geometry changes by looking at the roughness of the surface, roughness of the geometry, rather than the first dimension, second dimension, third dimension, degree by integers. But the roughness is not integer. So it says the similarity of the network, you expand, you contract. However, people start to ask, is that repeatable? Is it similar, same? The next is the British physicist and mathematician Penrose. He, of course, goes into the big pictures, conforming cyclic cosmology. If he talks about a Big Bang and how the universe expands, how the universe contracts, and the never ends kind of domain. But at the same time, the beauty is he used a simple example. Nobody has touched that before his time. Is by taking a diamond shape of geometry in a flat surface, no curvature involved, a flat surface. He fits into that diamond, into that flat geometry, and guess what? He mathematically achieved every single crack, every single continuity is filled without the discontinuity. But the question comes back is it still continuous? The answer is yes, continuous, but not purely periodic. People think our mind locks into a geometry is a periodic, perfect periodic, repeat itself. You have a certain period or the pitch or this kind of thing. And that pitch can be even talked into infinity. That is the nature of our geometry. So come back, look at this, what is the technology available and what is practical. And we need to look at the contraction and expansion technology, and also based on the cost to deliver a reliable product. So let's take a look. So this is pretty common. We are now talking about very fancy technology, nonlinearity or quantum bit, all those kind of things. We talk about those fundamental is the AWG and the thin film filter and edge drop, and also this kind of thing is also involved with the fractal geometry with miniature microscopic kind of a component with the quantum dot and quantum dot amplifier. You could also create some kind of edge drop. And the piezo technology right here, using the vibration, excite all of the vibration and give the motion sensor and the RFID. All those are available. But how can we put together to deliver a solution which will be more practical? So what we have accomplished by Foton is the network application we believe is need. It will go for high density. That's the nature eventually. And the high density optical intelligent panel with software driven network using our Peacock. And this is still goes into that is how can we be more practical and to deliver that solution. In other words, each junction become visible. So the building block, I go quickly, is a passive optic component. We have it, we manufacture those. And also we have the high density high quality cables, patch cords, those are building block very necessary. We have a tray chassis frame, and we have an OSP box supporting all those parts put into it. And also we have NG-PON2 and optic transceivers. And recently we have our Internet of Things hardware, software tapped and monitored. That's the capability. So look at our family chain. For the product line, we have connectivity, passive, active. Based on these three as a triangle is the baseline to building a fractal geometry. And we can interchange all the parts. And we have the high density fiber management system. And we have the passive component, WDM. And also we have the PDs and the PD arrays. And we have all the pound extenders. By using all this, we can put all the jig puzzles into one tray. And basically, we can have all those tapped passive component packaged into manufacture with high quality. And of course, I'm not going to read through this. And the beauty is we have the CWDM, WDM, and not only we have the traditional 3 dB couplers for the passive for the pounds, but also we built into, we play the game for fractal geometry is for prime numbers, we can go for 1 to 3 dB, not 3, 1 to 3 splitter and go for 1 to 12, 12 to 24 kind of splitter, and all packaged together, and the bottom line is high quality, like I mentioned. The high quality is past the vibration and the temperature cycle, lifetime, service lifetime test. And those are being tested in our factory by Telcordia, and we're very confident on that. So look at the building block. So building that, we have the basic tray, 1 RU. We can deliver 144 ports, and that's the minimum. We maximum, if we use this even special new connectors, we can even do much better. And of course, we put all the things in there. It's a fat finger proof. The principle is when you want to touch it, you can completely relaxed. But if you don't want to touch it, it can be compressed. And that's almost in the macroscopic system versus microscopic system. Microscopic system, you talk about, it's just Heisenberg uncertainty principle, you touch it, destroy it. But we are the reverse. On a macroscopic system, if you want to touch it, it's completely relaxed. But if you don't want to touch it, it compresses into the minimum. It's in its geometrical form. So all these things, if you want to have fiber shuffers, we can customize any combination you want, put it into a special termination. And at the end of the day, we have a big, massive frame which can terminate 6,000–7,000 terminations. And look at now next is look at the OSP reality. For those of you had experience for working in an outside plant, I'd like to show you, and I'm sure we're familiar with it. Those are called a cable vault. And of course, sometimes you have a small one, and sometimes you have a very big one, and that things can get very messy. And of course, the handhold, and the handhold prepared for termination, and the manhole. Those things are the reality in the field. So what we have built a dome. The dome can be installed under the ground or above the ground, whatever you want. But the beauty is we use the fundamental geometry is when not only the patch panel itself can be compressed, it can be expanded. We also use the fundamental geometry called Peacock wing. Doing the termination is one part. Also doing the fiber management is another challenging part. You don't want to tangle the spaghetti or kind of thing and end up with you cannot trace anything. So if you look at our installed the patch panel, the whole cable is in the Peacock wing. You can open it up, 100% visible, 100% can be accessed. But you don't want it, it shrinks and then becomes a dome, compressed into a dome, and very friendly, and also IP68. Basically, dip in the water for a month, it's still okay. You take it out, you drip the water out, you open it up, everything is inside is complete dry. So this kind of application, we can put a splice tray, any kind of passive optic component on it, and the Internet of Things. The next step is look at building the network of OSP. And of course, you have buildings cover the residential area, and the cable runs with the water pipe, all those kind of things of course, have followed the regulations. And also the microcell. And those things is all outside of plan. So what we have the optical distribution panel, and this is above ground, can be installed above ground on a pole, and that can support a 288 or even higher terminations. With all the passive inside, guess what? All the fiber management is on the side. Inside is all accessible. And then we have the Peacock design. We multiple layers can install in a pole. And guess what? Multiple layers. Without a Peacock, if you want access to it, it's all jammed. So what we have is we can spread out 3 layers or 4 layers, your hand still can access to it and get it connected out without disturb the adjacent channel. And the dome shape, we can have the tray slides out. Once it slides out, everything is accessible and very friendly. And the last thing is you have the big data center, central office, and we have the Peacock frame. Every single function can be embedded into it. And this is a jiggle puzzle, can be optimized. Any application you want, we can put into that. So what is the last thing is goes to the residential area. And I agree, not every single node is fiberized. Sometimes you have use wireless, sometimes use the fibers. This is all called optimization. But our solution build, it fully fits into this type of topology. And the invention is this part is we can slide in. Once we have end face touched, we register the connection. And of course, there's more detail we can talk about it. But I just give a conclusion. So the summary is we're building a future fiber cable termination infrastructure. Is very challenging task, but it is absolutely necessary. The 5G is revolutionary, which brings new challenges, but massive opportunities for everybody here. Our network architecture is very fractal. We have to respect the nature. And to have the capability of monitoring is the key for the healthy network and all its services. The optical intelligent panel will be an essential building block next to the physical layer, where the hardware, software, and application are all in full union. We are in the driving seat, of course, for innovation, implementation, and we can work together for the technology advancement. So what I propose is let's work together for our future, and our future has no boundary. Thank you so much.
Thanks, David.